IoT device communication. Today I'll be talking about machine-to-machine communication as it pertains to IoT devices, and how the protocols used as well as the hardware used are specifically tailored for IoT devices to foster efficient communication. Transferring data from one embedded application to another in a fast, reliable, and secure manner can oftentimes be a challenge. As such, the protocols used to transfer data from one IoT device to another, or from the devices to a server, must be lightweight, reliable, and low latency. Today I will discuss two main categories of IoT protocols: device-to-server protocols and device-to-device protocols. In cases where devices need to directly interface with each other to transmit and receive data, they are likely to be using the Data Distribution Services Protocol, or DDS. Other times, devices will upload their data to a server, which then processes the data from multiple devices, in which case the Message Queuing Telemetry Transport Protocol would be used, or MQTT. One important thing to recognize about the Internet of Things is that it is comprised of millions of devices that do not have the same resources that a normal desktop computer would have. This means that they do not have the same battery power or energy resources, nor do they have the same bandwidth or the ability to transmit data that conventional computers would have available to them. As such, the protocols used must take this into account and make things as lightweight as possible. Another important thing to recognize about these devices is that they are often medical devices or monitoring devices that have a very small margin of error. What this means is that these devices must be extremely accurate at all times due to the serious nature of their use. An example of this would be many devices monitoring the perimeter of a vestibule for chemical levels. Each one of the monitors must be able to accurately and quickly transmit its data back to the main server so that it can detect if there are any discrepancies in the levels from what they should be. As soon as a discrepancy occurs, it is very important that it is immediately alerted. Otherwise, you risk serious danger. When devices must directly send data from one device to another, or even from one device to thousands of others, a common choice is the DDS protocol. DDS employs a P2P architecture to directly send and receive messages from one device to another, and can deliver millions of messages every second. This provides data-centric connectivity from one IoT device to another. Another important aspect of DDS is that it is OS and programming language independent. This means that it is compatible with any number of operating systems and any number of programming languages. Depending on the device, some may not be able to handle all the overhead that DDS requires due to the lack of available bandwidth and energy resources. In these instances, a more lightweight version of the protocol that runs over UDP instead of TCP is available. However, in exchange for the faster data transfer and lower overhead, you are sacrificing reliability. This can be acceptable for certain types of applications that stream multimedia, but in many cases, reliable data transfer is a must. In device-to-server communication, the MQTT protocol is a common choice in Internet of Things devices. The MQTT protocol runs over TCP/IP and is responsible for dictating how data is transmitted between a client and a server. It is used in instances where data must be collected by the server from multiple devices so that it can be processed together. It is based on a publish-subscribe architecture, which sends control packets back and forth between the client and the server to do things like connect, publish, subscribe, ping, disconnect, and many other things. One thing that makes MQTT so fitting for the Internet of Things is that it is very careful about expending resources. In fact, it gives very few control options so that it can stay as lightweight as possible. Packet headers are kept to a tiny 2 bytes despite the fact that their payload can be up to 256 megabytes. This decreases the amount of data that the device must transmit and allows routers and link layer switches to process the packet much faster. Since disconnects are fairly common with these types of portable devices, MQTT also has a feature known as last will and testament. This feature allows you to specify a message that is essentially waiting for the client to disconnect unexpectedly, and then when it does, the message is automatically published. This can be very important in life-threatening instances where every second counts, such as notifying emergency services that a pacemaker has stopped working. With so many different devices and different manufacturers, it can be hard to find a standard that all devices use. But due to the fact that MQT is an open protocol, it makes it very easy to get the majority of developers to implement it as their device-to-server protocol when creating embedded applications. It is not only the protocols used that decide how efficiently a device can transmit its data. The technology used in the link layer of an embedded system is going to also play a part in how efficiently devices transmit and receive data. IoT devices are able to make use of Wi-Fi and Bluetooth, but a third option called Zigbee is specifically tailored to low-resource IoT devices. One of the strengths of Wi-Fi is the great range that it provides. Devices can transmit data to essentially anywhere else in the world. However, this comes with its drawbacks. Wi-Fi consumes a large number of resources. Take your phone, for instance. Oftentimes, your phone is connected to Wi-Fi, and you'll notice that you have to recharge it multiple times a day. Zigbee, however, is made specifically for low-resource devices. It has a very limited range, though. Zigbee is defined by IEEE 802.154. It is used to create localized personal area networks for devices that run on low battery, specifically IoT devices. The specifications defining technology for Zigbee are simpler and less costly than other personal area networks like Wi-Fi and Bluetooth. Some examples where Zigbee would be used are wireless light switches, electrical meters using in-home displays, systems for traffic management, and other industrial and consumer equipment requiring short-range, low-rate wireless data conveyance. Due to the low power consumption, Zigbee's transmission range is limited to just 10 to 100 meters, otherwise known as line of sight. One downside is that due to this close proximity of devices, multiple Zigbee devices can sometimes interfere with each other, compromising that data transfer.